welcome to another exciting season of Saturday Physics for everyone. So we have a great lineup. So we're going to have nuclear proliferation, nanoelectronics, and the swimming bacteria. So in 2 weeks, Professor Dana Cox will tell us about visualization in science, technology, and arts. So hope you will join us. Today, we are very excited to have Professor Brian Fields to give us a talk. He spent majority of his career in Midwest. First, he got his PhD in the University of Chicago. Then he went to Paris a little bit. He came back. He was in University of Notre Dame. Then he was in University of Minnesota. So he came here in 1998. So almost 20 years. And so he has a very wide research interest, from Big Bang to exploding stars, from dark matter to neutrino astronomy. And if you are a long-time attendee of these lectures, you may have seen Professor Fields give a talk maybe 2 years ago with the same title, Star Attack. But this is actually a new talk. It's a sequel. It's our sequel to Star Wars series. So he's going to show you a lot of new and exciting new results. Let's welcome Professor Fields.
There we go. Thank you, Liang. So, well, good morning. All right. So it's a beautiful Saturday. Normally, I would be home asleep, so I really respect the fact that you guys are all here. So there's a lot to talk about, but I wanted to say a couple of things first. So as Liang said, this is the 25th year, the 25th anniversary, the quarter-century anniversary of Saturday Physics. That's an amazing thing, and is it not? And this doesn't happen by accident. Lots of people have to get up early on Saturday to make this happen. And the founder of Saturday Physics and the person who really made it happen is sitting right over here being shy, and that's Inga Carlino. Wave, Inga. So Inga is literally responsible for our being here today. She's an accomplished physicist with a long research record in high-energy physics and cosmology. But she's also animated by her drive to bring physics to the people, physics to everyone. And she's the Jedi master of this. And she has the amazing ability to inspire people to help. It's like a Jedi mind trick. And so that makes her the godmother, right? She makes you offers you can't refuse. Well, couldn't you just give a lecture? And then you just can't say no to Inga. So she's not only responsible for getting started Saturday Physics, but also Science at the Markets. If you go to the wonderful Urbana Farmers Market, there's science there, and that's Inga. Physics van she helped get started, any number of things. And I should say Inga is also a great friend and one of the most welcoming people that made me feel at home here almost 20 years ago. And Inga's already, quote, retired for several years, but she's now threatening to become actually like a retiree and travel the world. So I just wanted to say it's amazing she's done this. And by my calculation, a conservative estimate is that 15,000 people over this time have seen Saturday Physics. It's truly an amazing thing. So please join me in thanking Inga. All right, so I'm also in the astronomy department, and so we just had an amazing thing happen. So the cosmos has done an amazing thing for us. We had this eclipse. So quick show. So I want this talk to be interactive. You're supposed to ask questions, because if you don't understand what's going on, that means I'm doing something wrong. So please ask questions. I'll give you opportunities to ask questions, but you can ask other times too. But first things first, first chance for participation. So who saw the eclipse? Show of hands. Oh, I'm seeing all the hands. That's awesome. And did anybody have an opportunity to see totality? Oh, I'm still seeing lots of hands. And of those people, so if you saw the eclipse, was it awesome? Yes, it was totally awesome. And as you know, if you didn't get a chance to see the eclipse or didn't get a chance to see totality, the good news is there's a do-over. In 7 years, it's going to once again come through the great state of Illinois. Actually, it'll start in Mexico, go through Dallas, go through Illinois, and in Indy, go all the way up to Buffalo, over Niagara Falls, and to Canada. So it'll be the great North American eclipse. And so for the young people, 7 years seems like a long time, but I promise it will go by very fast. And if I could take a moment to philosophize, the eclipse is a reminder that we are citizens of the cosmos. So we Earthlings do not live lives that are independent of the cosmos, and once in a while the cosmos intervenes in our lives, and that's a theme we're going to have more of in this talk. So that brings me to my talk. So I want to talk about what happens when stars attack. And I don't mean ill-behaved Hollywood actors. I mean actual astronomical objects. And so what I want to tell you is this has occurred. We know that there have been recently, from an astronomer's point of view recently, supernova explosions, more than one, that have happened near the Earth. And the way we know it is by looking at crazy rocks like this and finding radioactivity. And by the end of the talk, I hope this crazy statement will make sense. And I should maybe say, too, this is a nice example of how science works. So there's science there's all kinds of aspects to science, and there's science for different styles of how you do your work. So sometimes we work on subjects we understand really well with great precision, and then we peer even deeper to understand the problem even better and to find ever more subtle and beautiful effects. And there are plenty of people in this department that do that. And some of my work involves that kind of work as well. But sometimes it's the Wild West. We're trying to understand something that's totally new, and we're just trying to get a sense of the lay of the land. Where's the oasis? Where are the cactus? Where's the rattlesnakes? And that's what this is. So this is work that I started out more than 20 years ago as a graduate student. And initially it was just a hobby. It was just a fun thing I did. There was sort of a crazy idea, and it wouldn't be good to do it full time. But over time, over the past 20 years, and particularly in the last couple years, it's become super interesting, and I hope you see why. All right. So here's the game plan. I'm going to talk about what happens when stars attack, supernova explosions near the Earth. So the first thing I got to do is tell you what a supernova is. So they're really bright. They're brighter than 1 billion suns. And so I'll talk about what it's like to see a supernova, what the data is, what astronomers can tell us about supernovae. But then I want to get under the hood. I want to tell you how supernovae work. What's the physics of these amazing, spectacular explosions? And tell you how supernovae are the deaths of massive stars that are celebrities of the cosmos. And like other celebrities, they live extravagant lifestyles and then flame out and die spectacularly. And then we'll bring the problem a little closer to home, and I'll talk about what happens if one of these explosions happens near you. And there comes a point where it's not funny anymore, and we'll talk about how far away that is. And then finally, we'll do supernova archaeology. So we'll look at debris from the bottom of the ocean that will tell us that that supernova explosions happened near the Earth recently. All right. So first things first, let's talk about supernova explosions, and we'll talk about beautiful images like this. That's part of the beauty of astrophysics, by the way, is images like this aren't just beautiful, they're data. So, all right, very good. So to start off, this is our first Saturday physics. So to start off, it's a nice opportunity to give you a sense of how astrophysics works. So let's go through a little exercise, and let's talk about stars. Okay, so I'm going to give you a few facts. It's Saturday morning, you're waking up, the coffee's setting in. So let me just start by telling you things you already know. Be a little patient, I'm trying to get somewhere with this. So I know you know this. Stars, like the sun, constantly lose energy. That is, they're constantly pouring energy into space, mostly in the form of the light that they emit. Duh. And that's, of course, what warms and illuminates the Earth. So stars are forever emitting energy in the form of light. Very nice. We all knew that. Also, stars, like the sun, but all stars, have a finite mass. All I mean by that is they have a not infinite mass. Duh. But because they don't have an infinite mass, that means whatever their fuel is, I don't even need to tell you what it is. Turns out the fuel is for nuclear fusion, but it doesn't matter yet. Whatever the fuel is, they don't have an infinite amount they only have a finite amount, which means they have a limited energy supply. It's like their battery is not infinitely big. Fair enough? Duh, once again, no big whoop. But then finally, it is also true, we're in a physics department, so we know that energy is conserved. There's no free lunch. You can't just create energy out of nothing. All you can ever do is transform energy from one form to the other, maybe move it around from here to there, but energy is neither created nor destroyed. That's what we mean by energy is conserved. So, all of these, none of these are particularly new to you. You didn't have to wake up early on a Saturday to hear them. But if you string these three ideas together, it tells you something interesting, namely, this is your turn now. Energy and mass, sorry? So energy and mass are related because somehow the mass in the sun is generating energy, and we'll talk about how that is. Thank you. So that means the sun is going to die eventually. That's right. So stars cannot live forever because they have a finite supply of energy. They're pouring it out into space. Eventually the supply is gone, and that means they will stop lighting up. Stars cannot live forever. So let me say that in a little bit more pointed way. That means all stars are going to die, including the sun. So here it is, a nice Saturday morning, and I'm now already telling you the sun is going to die. There's an important follow-up question you might, and I've basically proven it. This is like a mathematical proof. You can make this a mathematical proof. So that's a bummer to hear on a Saturday morning. There's an extremely important follow-up question you should ask. I've been told this. When? Yes, exactly. I haven't told you how long the sun will live. I just tell you it won't live infinitely. So the good news is the sun will last another 5 billion years or so, and it's already lived about 5 billion years. So the sun, like many of us, is middle-aged. So that's fine. So don't make any plans for 1 billion years from now, but otherwise, there are many things to worry about in this world. North Korea, hurricanes, the dying sun is not one of them. Yeah, please. Oh, yeah, there's a longer discussion we can have. Yeah, so the question was what happened, will the sun do bad things, or actually we have a ringer who knows the sun will do bad things before 5 billion years. It'll actually boil the oceans in about 1 billion years, so truthfully you should already start to think about that. Don't mark your calendars 1 billion years from now. One last point though, before we depart. So stars, all stars must die, stars don't live forever, and yet the night sky is filled with stars. So that tells you something else. They don't live forever, and yet the sky is full of them. There's so many people giving good answers, I couldn't hear them all. So what that tells you is they can't live forever, and yet they're in the sky now, which means they had to be born at some point. They can't have hung around forever. They had to be born, and that means stars are born, live, and die. So like people, like dogs and cats and cockroaches, stars have life cycles. And that's an amazing thing. And notice how cool it is that we started with these 3 trivial facts, and we come up with this really interesting conclusion just by stringing together these interesting facts, and using a little logic and a little imagination, we learn that stars have life cycles. That's an amazing thing, and that's an idea of how astrophysics works. You take some clever ideas and think carefully and see where it takes you, and that's what we'll do today. Okay, and by the way, the life cycles of stars is a specialty of Illinois. So people at University of Illinois study all aspects of the lifestyles of stars, from birth to middle age to death. Okay, so now, please.
Do we know if new stars are currently being born?
Well, you bet we do, and that's a major object of study at Illinois and elsewhere. So new stars and new planets are being born today. It's an ongoing process. I'll have more to say about that, in fact. As a whole talk in itself, but I'll say a little bit more. So now let's talk about supernova explosions. So supernova explosions are not how most stars will die. They're only the rich and famous. They're the deaths of massive stars. Stars that are more massive than about 10 times the mass of the sun, or maybe 8 times the mass of the sun. It's a number like that, much, much more massive than the sun. And these are spectacular, as you'll see, but they're also rare. They don't happen that often. Most stars don't die this way. And they're crucial for life as long as you don't get too close. So they're a good thing, but you don't want too much of a good thing. So what do we see? First of all, let's gather the data. We want to do science, and science begins with data. So what do we see? These things are bright. Here's what I mean by bright. So here's an image. This actually is a Hubble telescope image. And so there are two main things that draw your eye in this image. So you see this, this swirly thing with this diffuse light and these interesting bands here. So that is a galaxy. And what you're seeing here, so it's not our galaxy, it's a galaxy like ours. And what you're seeing here, all the light, the galaxy is so far away, even the Hubble telescope can't make out the individual stars. The light from the stars all smears together into this haze. And what you're seeing here is the combined light of something like 100 billion stars. That's about how many are in our galaxy, too. And so the light you see here is 100 billion stars worth of light. Okay, good. That's interesting by itself. We could have a whole talk about galaxies. But I want to draw your attention to this. This is a star on the outskirts of this galaxy that's exploding as a supernova. So that's a single star dying as a supernova. And the point of this exercise is if you kind of squint, you can see the total amount of light here is about equal to the total amount of light there, which means while it's exploding, this star is about as bright as 100 billion suns. Yeah? Sorry? Oh, yeah, the dark bands, oh yeah, that's interesting. The dark bands are because interstellar space is not empty. It's got pollution in it. It's got actually the guts of previous dead stars are in there, and then they block some of the light. We'll hear more about those guts in just a minute. Good eye, thank you. Yes, sir? Sorry? Oh, yeah. So if the star were closer, it would be brighter, but actually this star is a citizen of this galaxy, and so it's the reason it looks brighter is because it really is a lot brighter. But if it were closer, that's exactly right. And astronomers have to worry about that. Thank you. That's an excellent question. All right. So supernova explosions are super bright. But they don't stay that way forever. They change rapidly over time. So they grow to a maximum in a few days, and then they dim over the period of weeks and eventually are gone. In fact, this image was taken in 1994. If you look there now, you wouldn't see anything in this spot. Okay, and to give you a sense of how this works, here's a supernova in another galaxy. There's a little movie here where I'm going to let it loop. So here's another one of these galaxies, and boom, there's the supernova. And it comes and goes, and it fades away, and there's other stars and junk here you see, and they don't fade away, but the supernova comes and goes. And then this shows you the brightness as a function of time. So you can see it gets brighter and dimmer, and then this is the different colors that come out of it. Okay, so it takes, so over a period of a few months, it comes and goes and then is gone. Okay. And what happens is a shock wave is launched. This is an explosion. A shock wave is launched generating fast, ultra-hot gas. And this is the remains of an exploding star where its guts have been thrown out into space. And you can see these little tendrils of gas. This is thousands of years after the fact. And this pink color, for the experts in the room, that's telling you there's a lot of hydrogen here, which used to be inside the star. Okay, so these are really spectacular events, but they are rare. So here's what I mean by rare. So again, they're only massive stars that die this way, and most stars are not massive. So in fact, fewer than 1% of stars die this way. In fact, it's more like 0.1% of stars, 1 in 1,000. And no supernova has been seen in our galaxy by humans for 300 years. The last one we know of in our galaxy was 300 years ago. So as we already discussed, it's a bummer. The sun will die. But not this way. It won't be an explosion. This whole other talk, how the sun will die. It's interesting. It will get your full attention, but it's not an explosion. And not for billions of years. So sleep well tonight. Like I said, there are things to worry about in this world, but please don't go worrying about the sun dying. Okay. So now let's talk about supernova explosions. I said they're very rare. The last one in recorded history was 300 years ago. The last one in our galaxy was 300 years ago. But there were people around even then, and people wrote things down. So we actually have recorded, written observations of supernovae. So a famous example was in the about a little under 1,000 years ago. So not Y2K, but Y1K. In the year 1054, a very interesting thing showed up in the sky. Surprisingly, you could have seen it from Europe, but there's no written record, and it's a puzzle why there is no written record in Europe. They should have been able to see it. In China, they did see it, and they recorded, so I don't read Chinese, but this is one of the ancient documents from Chinese, and they recorded, this is the information, that's sort of their journal, that's their blog, and this is where they're saying where it is in the sky. And they had this beautiful term, I don't read this, but I'm told that this says guest star, which I think is a very beautiful term. So, and in the United States, in the Southwest, the Anasazi people who live in New Mexico, they saw it, and there's this interesting rock painting. I don't know how well you can see this, but there's this star-looking thing, a crescent moon, and a hand. And I'm no anthropologist, but I'm told that the hand is a way of saying this is a significant thing. And it turns out that if you follow back from the Chinese information about where and when this was, it should have been near a crescent moon, so it's pretty sure that they saw this thing as well. It's peculiar that there's no European record of it. Yes, so exactly. So there's some discussion that it might have been not at the time. That was back when people thought that the heavens were supposed to be unchanging. This was this old Greek idea. The heavens were supposed to be unchanging, and so it was not politically correct to have the things come and go in the sky. It's also known that weather in Europe is pretty crappy. So now, if you look at this part of the sky, you let the Chinese tell us where to look in the sky, and you look there now, this is what you see. So this is called the Crab Nebula, because it kind of looks like a crab, and this is the remains of an explosion. So 1,000 years later, this is what you see. The guts of the star are strewn out into space. So another historical supernova that I particularly like was then 500 years or so after that, and that was seen by Tycho Brahe, which is one of the great founders of modern astronomy. So my idea of modern is 500 years ago. And here's his diagram that he wrote. Back then, their blogs were on these things called paper. And so he wrote on paper where this thing was. And they wrote in Latin back in the day. That was the style of the time. And he called it a nova stella, which is his way of saying a new star. And so that's his diagram. And if you look in that location now, it's in the constellation Cassiopeia. And if you look there now, this is what you see. It's beautiful. So here's a modern view, but done with X-ray visions. You have to do this from orbit. We've got telescopes that see X-rays, and this is what you see. So this thing is so hot that it's glowing, not blue hot or white hot, but X-ray hot, which means it's millions of degrees. So, okay. So Tycho, like I said, he wrote his blog on paper. Back in the day, they wrote their blogs on this stuff called paper. And so he wrote a blog entry about this. And there's Tycho. He was this wealthy nobleman, so he could afford to do astronomy. He was even before there were telescopes, but he was still a great astronomer. And he wrote down an account of what a supernova looked like. So it's sort of like our blogs talking about what the eclipse was like. He saw something spectacular, and he wrote about it. So let me read it for you so you can take it in. So he says, on the 11th day of November, in the evening after sunset, I noticed that a new and unusual star, surpassing other stars in brilliancy, was shining. And since I had, from boyhood, known all of the stars of the heavens perfectly, it was quite evident to me that there had never been any star in that place of the sky. I was so astonished of this sight, a miracle indeed, one that had never been previously seen before our time in any age since the beginning of the world. I love that quote. Okay, and one of the reasons I love this quote, first, I like his enthusiasm, but I also like that he gets some things right, but like all scientists, he also makes mistakes and he gets some things wrong. So let's first give Tycho credit. He was a brilliant astronomer. What did he get right? What does he say here that's correct? Yeah, it was very brilliant. Good. Certainly was. So yeah, so he said he hadn't seen, there wasn't anything in that part of the sky before. That's also true. Anything else? Yeah, one other thing. Good. So he said it's unusual, that's for sure. It's certainly brilliant. And he also did know all the stars of the sky. He wasn't modest, but he was a really good astronomer. He did know the stars of the sky perfectly. Okay, but now it's no disrespect to Tycho to say that he also made some boo-boos here. So he got a few things wrong. So what did Tycho get wrong? Never been previously seen before in our age. How does he know that? He doesn't have any evidence for that. That's just being arrogant. I just showed you 500 years before people had records of this. Good? There was a star there, exactly. So this was a change in the number of stars, but instead of increasing the number of stars, it in fact was a decrease in the number of stars. So it was a change in the number of stars. This is what we refer to as a sign error. So he got the idea right. He just got the sign wrong. Very good. Very good. So good. And so yeah. So he said it was new and it wasn't new. There'd never been any star. You get partial credit, not the one you could see with your eyes probably, but there had been something there. And this was just arrogant. Okay. So all right. So far so good. You guys have been good about asking questions, so I don't need to prompt you so much. All right. Great. Oh. There you go. There you go. So that's right. So we should give him. Yeah. We shouldn't be too harsh on Tycho. Yeah. Oh, that's a good question. So he would have kept looking. I actually don't know what is in his blog after that, but no, he would have kept looking there. Like no way he would have not paid attention to that. But he would have. We know what he would have seen. He would have seen it fade away. There's even ways we can backtrack now and detect the fading, but that's a longer story. So I'll keep going. So now I've shown you a bit about what supernovae look like, and I hope you appreciate that they're gorgeous, but there's also amazing physics. So now let's get under the hood, that is, pop the hood and look underneath and see how the machine works. Let's talk about how supernova explosions work. So supernovae are the James Dean of stars, and the younger people might not know who James Dean is. The thing you need to know, he was this guy from the 1950s. He lived fast, he died young, and he left a beautiful corpse. And it's the same with stars. So to give you a sense, this is a Hubble telescope picture. So HST is Hubble Space Telescope. It's one of the early things. So this is, from 1995. And there's this beautiful picture they took. So in the constellation Orion, which is starting to become visible in the early morning, there's Orion's belt, there's his shoulder, there's his knee, and Orion's shoulder is this star called Betelgeuse, or Betelgeuse. It's this beautiful red star, and with your eyes, you can tell that it's red. You can tell it has color. And if you look at it with the Hubble telescope, it's no longer a dot. You see, it's one of the few stars that with even the Hubble telescope you can show is really spread out over space. It's not a dot. Here's the size of the star. Here's the size of the Earth's orbit around the sun if it were placed on the same scale, and the size of Jupiter's orbit around the sun, which means if we were orbiting Betelgeuse at the same distance we're orbiting the sun, we would be well inside of Betelgeuse. It's an enormous star. This thing is about 20 times the mass of the sun, which is a number known to be above 10 times the mass of the sun, which means this thing is going to explode someday. So someday this will explode, be a supernova, and change the face of Betelgeuse. Actually, the star down here, there's a blue star called Rigel. It'll do the same thing. Okay, so these stars live fast, so this star is pumping out huge amounts of light, and it will not live long. And let me say a little bit more about how that works. What's the physics of that? So the lives of stars, massive stars, but all stars, including the sun, the lives of stars are all about gravity. In fact, most of the evolution of the cosmos is about gravity. The life of a star is about gravity. In fact, a star is always fighting against its own gravity. I mean, after all, the sun has enough gravity to hold the Earth, Jupiter, all the planets in orbit, reaching out over space through the force of gravity and holding everything in orbit, and we should be glad for that. But of course, the sun also pulls on itself, and the sun has enormous amounts of mass, and so mass is the source of gravity, so you might wonder, why doesn't the sun collapse upon itself? Well, the reason the sun doesn't collapse upon itself, well, let's talk about that. So the sun maybe is too complicated, it's some crazy body in space, so let's talk about something a little simpler. Let's talk about a balloon. So a balloon, like the sun, is made of gas. The sun is made of gas. And the sun has gravity trying to compress the gas. The balloon doesn't have very much gravity, but it's got the balloon, the rubber in the balloon is trying to compress the balloon. And as you know, gas is compressible, so you can ask the same question. Wait a minute, why doesn't the balloon collapse down to nothing? It's not a trick question, you know the answer. Air pressure, right? The balloon is full of air, which exerts pressure, and if you push on it, it pushes back. And what happens is the balloon settles down to a point where the pushing in from the elastic force is the same as the pushing out from pressure, and it reaches a nice balance, and it's perfectly stable. Well, in fact, the same thing is true for the star, like a star like the sun, except it's no longer elastic force from a balloon, but the inward force is from gravity, the outward force is from its own pressure. Very good. So, and And the pressure is generated by the fact that the star stays hot, and the reason the star stays hot is it's billions of degrees at the center of the star, and there are nuclear reactions going on, releasing nuclear energy. And that keeps the star nice and hot and pressurized and stable. So now, that raises an interesting question. We already said stars can't live forever. They run out of fuel. So when the star runs out of its fuel and it can't generate more energy by burning its fuel, its nuclear fuel, then it can't stay hot, and then what would happen? It would collapse, exactly so. And so let's test that. So here we go. So what I've got here is some liquid nitrogen. So this is nitrogen, which actually you're breathing right now. It's 75% of what's in air. And liquid nitrogen is pretty chilly. It's minus 300 degrees Fahrenheit. So I'm going to pour a little bit onto this container. And you can see from the point of view of the liquid nitrogen, this room temperature pan here is very, very hot, so it's boiling. So it's really neat, right? So now this balloon is currently at room temperature. So let's make it at not room temperature. And there we go. So now, this is the same as a star running out of its fuel. So now we make the balloon lose its ability to be hot, and then the thing becomes very small. But if I take it away from the cold that's robbing its temperature and it gets warmed up by the air in the room, the really neat thing is it comes back. It's totally cool. And since it's fun, now we have this interesting shaped balloon. So let me show you, if you do an even bigger balloon, we can also collapse this one as well. So you can see the whole little wiggly worm is getting very unhappy. It's happy now, but it won't be happy in a minute, and you can make the whole balloon collapse. And so that's what's happening now. There it goes. Bye-bye. So, all right. So that's what happens to a balloon, and that's what happens to a star. So when the star runs out of its fuel, then it collapses in on itself, and it dies. So when its fuel is exhausted, just like the balloon, it can't fight against gravity anymore, and it collapses. But then, as it collapses, more and more matter is being crushed into a smaller and smaller place, and so that means the core of the star, the center of it, is getting denser and denser. It's getting more and more packed with matter, and it finally gets so incredibly dense it becomes the densest thing we know of, which is the same density as an atomic nucleus. Incredibly dense. It's like a giant atomic nucleus. And then finally it's so dense that it won't be compressed anymore. The nuclear repulsion of all the particles, of all the protons and neutrons, finally is enough to withstand the compaction. And then the star bounces off of this dense core, and the inward motion is translated to a shock wave that goes outwards, and that's an explosion. The details of this, by the way, are still being worked out. I made this sound simple, but believe me, it's not simple. So that's, again, worth a demo. So I brought a supernova. Don't worry, it's safe. So this is the Astro Blaster. You can buy these. I'm not trying to sell you, but you can buy them. So here it is. It works like a real supernova, and you know that because it's written right there on the package. And so the idea is, so these stars have different layers, and so actually the way this works is the very core of the star is the floor. That's the bottom layer. But then layers of gas above have lower and lower density, and that corresponds to the smaller and smaller balls. So I'm going to simulate the destruction of the star. Oh, that's good. I'm going to simulate the collapse of the star by dropping this, and then for safety, there's a little stick here, so only the small red ball will actually be able to leave, but then we'll see what happens when the thing collapses. So here we go. So the star is burning, 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 runs out of fuel, the core gets crushed to nuclear density, and then the star collapses, and there we go. And it goes careening across the room, and that wasn't even a particularly vertical fire. So you get the idea. As the star bounces, the big ball bounces up, then hits the little ball, and since it's moving even faster because it has smaller mass, so it goes at bigger velocity, momentum conservation, and that continues until the top ball goes at very high speeds, much higher speeds than it fell. So, very good. And so then the star leaves a beautiful corpse. So we crushed the star to this incredible density, the density of an atomic nucleus. We made a giant atomic nucleus, which was like 10 to the 57 neutrons and protons, and that stays behind. That's what the cinder is. So that's a neutron star, and sometimes actually if you compress it too much, it collapses and becomes a black hole. This is a good way to make a black hole. Not always, but sometimes. But actually most of the material doesn't stay at the center. Most of the material, like with the astroblaster, is thrown out into space. And so what you see is this. So this is an X-ray image of a star that exploded 300 years ago. I told you 300 years ago was the last time. There's a crunchy object, a dot in the center, but most of the guts of the star were strewn out into space. And you're seeing them again in X-ray vision. So there we go. And the fact that it's X-ray vision means it's millions of degrees, and this is 300 years after the fact. So 300 years after the fact, it's still millions of degrees. And then this is older still. So this is gas from a supernova thousands of years ago, and it's still very hot, and it's full of all kinds of interesting elements, which is what's making these interesting colors here, sort of like a neon light. Oh, please.
Do we know when, can we predict when Betelgeuse will?
Oh, thank you. That's an awesome question. Yeah. So can we predict when Betelgeuse will explode? Oh, that is such a good question. And that's a super interesting answer. The answer is no. It turns out, and that's a somewhat disturbing answer. It's one that I'm very interested in. So it turns out in the last phases of the star's life, when it's doing its last phases of burning, everything happens so fast. In fact, the final stages happen over periods of days. It happens so fast, all at the core of the star, the outside of the star doesn't know. And in fact, it's not just true for the last days, it's for the last 100,000 years. So you can't tell by looking when a star is about to explode. As far as we know, people are still actually very actively working on this. And so you don't get any warning. And that's not necessarily a good thing. And I'll end up telling you we don't have any, Betelgeuse is not close enough to be dangerous. If we did, there is one way. The stars generate these crazy particles called neutrinos. We're about to talk more about them. If you could, and it will start to generate them prodigiously even before it explodes. And if you had one near you and you were motivated, you would build a really big detector to find those neutrinos. And that's how you would know. It's a great question. That's actually a subject of active research right now. Very good. So this brings me to the circle of life. So we ask a little bit, we determine stars have life cycles. Here's the life cycle. So let me say a little bit about how this works. The galaxies in the universe contains gas. The gas condenses sometimes into these huge, amazing clouds. These are called the pillars of creation, a famous Hubble telescope picture. And these clouds of gas are very cold, and because they're very cold, they're subject to gravitational collapse, just like the balloon, and they generate new stars. We see this as an ongoing process. And then, most stars, like the sun, don't die in an explosion, they die other ways, but once in a while, massive stars do die as an explosion. That's an example of before and after on the same picture. And then what's left behind is this interesting crunchy center, and then the star ejects everything it just made into the gas around it. And so the universe is enriched by the heavy elements that the star makes, because that's mostly what it makes, is heavy elements. And so, and then we keep going around, and as we go on, the material, the gas in our galaxy is forever being enriched by the deaths of stars, and they make the elements we're made of. Yes? Oh, yeah. So, yeah, that's a good question. So the stars, so we're about to talk about this. The stars are mostly, are born, like the sun, are all born mostly made of hydrogen, and when they burned about 10% of it, that's when they explode. So they still are mostly made of hydrogen when they explode. So we are made of the nuclear ashes of stars. Most of the elements we're made of were actually forged in exploding stars. We are made of the nuclear ashes of stars. And I should say a little bit more about that. So in the star, what's generating energy is nuclei, not just atoms, but stripped atoms that are in nuclei are colliding. It's 1 billion degrees. That means they're colliding with each other at very high speeds and high energies. And they produce new kinds of elements. It's alchemy. And most of the nuclear reactions in stars produce healthy, stable atoms, and kind of atoms that you've heard of: iron, oxygen, silicon, the stuff we're made of, carbon, oxygen. But in the blizzard of nuclear reactions in the star, some unstable radioactive atoms are always produced. There's no rule the stars only make stable things. They also make radioactive things. And later in the Saturday Physics, in a few weeks, we're going to be hearing more about radioactivity, so I won't say a lot, except that the nature of radioactivity is there are some nuclei that are just unhappy. They're unstable. It happens to people. You have a bad day. And so they're unstable, and they want to settle down and become stable. And the way they do that is they decay after a certain amount of time, and they go to a more stable state. So they change their identity. And it's all good, but and different kinds of radioactivity, different kinds of isotopes decay after different times. And so to give you a sense for that, we have a little bit of radioactivity here. Don't worry, you're safe. We have a small amount. And let me see if I can do this right. Here we go. Okay, so there you go. Up there, we've got a little counter that sees when there's any radioactivity around. And then in this box, if I can do this competently, we've got very small, safe amounts of radioactivity, which nonetheless are stored carefully because, it's radioactivity. And so there we go. So let me get out just a little bit. They're enclosed in plastic, sanitized for your protection. And so I've got a Geiger counter here. So first of all, if you look at the ticks, it's now going way up. Let me turn on a microphone. And there you go. So this is So this is a radioactive form of cobalt, of the element cobalt, most of which is perfectly stable. You can have jewelry made of it. It's all good. But this is a radioactive version, and it's busy decaying to iron, I believe. And there you go. You can see it's merrily decaying away. So every little click is one cobalt nucleus, boom, decaying and becoming more stable and having a happier life. So that's an example of radioactivity. And that's a small amount of it. It's not dangerous. I wasn't scared to handle it, so don't worry about that. But the point is, stars make all kinds of radioactivity when they explode. Not much of it, but they make some. And just to give you an example, the solar system was born 4.5 billion years ago, and there were traces of radioactivity when the sun was born. And it actually tells us that there was probably a supernova nearby before the sun was born. Also, today, let's see. Yeah, let's do that. Get back to the... Okay, and today, our galaxy contains traces of radioactivity. And I'm particularly fond of this because we can take a picture of it. So it turns out that our galaxy, so this is a map of our galaxy as seen by us. We live inside of it, so it looks like it's a flat disk like a Frisbee. We live inside of it, so it looks like a strip on the sky. And it turns out there's certain kinds of radioactivity. I'm not sure if the cobalt does this, but there are certain kinds of radioactivity. This is actually a kind of aluminum that's radioactive. And when it decays, it emits a little flash of light, but a very powerful flash of light you can't see with your eyes, called a gamma ray, and a very specific gamma ray. And so if you tune to that gamma ray, you see that our galaxy is shining with this crazy gamma ray, which tells you that there is unstable radioactive aluminum made by exploding stars is in our galaxy and merrily decaying away. So our galaxy contains radioactivity. And that also tells you that it's another way to know that there's ongoing star birth and death, and the stellar deaths are making radioactivity. So it's very nice. Okay, great. So now we know a bit about the supernovae are awesome to look at. We know a bit what they are. They're exploding stars that have tons of nuclear reactions and throw their guts into the universe. And now we bring the problem a little closer to home. So what happens if a supernova blows up near the Earth? So this is a supernova that was kind of near us. It was a little baby galaxy next to us called the Large Magellanic Cloud. That actually is not that's not nearby from my point of view. Yeah. Oh, so the radioactivity is, so there are nuclear reactions in stars, and I could go on and on about, there's all kinds of nuclear reactions that go on all at the same time, because the star is made of all kinds of nuclei that are always banging into each other. That's just because they're super hot, they're always banging into each other, and different combinations sometimes make stable things, mostly make stable things, but once in a while make radioactive things. The kind of radioactivity I'm going to talk about, especially called iron-60, is made when there are these particles called neutrons, and those get gobbled up by iron, and the iron keeps eating neutrons until it makes the kind of iron I'll be talking about. But there are different ways. There's a long list of different ways radioactivity is made. Oh, so yeah, so uranium is, so there's a longer story. We don't need uranium for today's talk, but I could give a whole talk on it. It's a super awesome question, and that would be a whole talk in itself where we get uranium. We think it's from neutron stars colliding with each other. It's an awesome question that's like a super hot topic right now, but we don't need that talk for now. I'll mention plutonium, we'll come back to it. Okay. So now we want to bring supernova explosions near the Earth. So these are cosmic weapons of mass destruction. In these dark days, I don't mean to make jokes about weapons of mass destruction. They're not funny. It's just that that's the only thing to compare them against. And again, in the Milky Way galaxy, we have about one supernova a century. And so here's a galaxy that's not ours, but probably a lot like ours. And we live somewhere out here in the suburbs. And in an entire huge galaxy, you get one supernova about every century. And so, they aren't random, but you could think of them as kind of randomly strewn across the galaxy. And generally, they happen far away. So they're spectacular but harmless. They're fun to look at. It's all good. And right now, I can tell you there are no massive stars very close to the Earth and close enough to be dangerous, so please don't worry about exploding stars. But over the history of the Earth, it is very likely that there were explosions near the Earth over 4.5 billion years. And that brings you to the question then, what happens if a supernova blows up near the Earth? And the Surgeon General has warned us supernovae, like smoking, are dangerous to your health. Smoking's bad, supernovae are bad if they're near you. They're a biohazard. And so here's how it works. If the supernova is too close, then it's dangerous. It's not funny anymore. It's a bomb going off next to us. And the holy grail, or the unholy grail of this field, is to connect a nearby supernova to a mass extinction, one of these times in the Earth's history where there is a huge die-off of species. The most famous example that everyone knows about is the dinosaurs, and actually for some time people seriously considered the idea that a supernova was responsible for the dinosaurs. Turns out that's not true. A big rock fell on their heads, so it was death from above, but not from a supernova. But the dinosaurs were like, of the 5 major mass extinctions, the dinosaurs were the least bad. So there are 4 other big ones, and it would be interesting if even one of those was caused by a supernova. Oh. Oh, I'll say that in a second. We're getting to that. Yeah, very good. So you might ask, because it's a fun question to think about, if a supernova blew up really close, what do you think would be bad about that? So, yeah, back. Yeah, so it's like lighting fireworks. It's like a bomb going off next to us. And so what kind of bad things might a supernova do, you think? Yeah. There would be. Very good. So it'd shred our atmosphere. Good. That's a good point. Yeah.
So who needs North Korea?
Yes, that's right. Right, exactly. So, as if we didn't have enough to worry about. Yeah. So, okay. So it turns out that these crazy particles called neutrinos from a supernova are potentially dangerous. The good news is that it turns out for these crazy there's a whole discussion of neutrinos, which I can't get into. Fortunately, the star has to be really close before neutrinos are a problem. But what actually is more damaging is what was suggested. The X-rays and gamma rays from a supernova, the really nasty ionizing radiation, it won't remove the atmosphere, but what it will do is it damages the ozone layer. We have this ozone hole in the atmosphere. A supernova doesn't create an ozone hole. It makes the ozone gone. It removes the ozone layer, wipes it clean. And that is bad because the ozone protects us from ultraviolet light from the sun, and if we remove the ozone from the atmosphere, the sun's ultraviolet light is unfiltered, and then the sun kills us because the nasty UV, you and I would put on a big hat and sunblock 2000 and try to get on with our lives, but little critters, phytoplankton at the bottom of the food chain can't do that, and they get killed off, but they're on the bottom of the food chain, and so it's bad for everybody. And then when you put all that together, then you can answer the question of how close is too close. And the minimum safe distance is about 30 light years. That's 10 parsecs for the experts out there. And so what that means is that's the distance light travels in 30 years. That's, for an astronomer, that's really close. That's a very nearby neighborhood to us. And so the good news is there are no threatening stars in that distance. So again, please sleep well tonight. Worry about North Korea, not this. Okay, so let me finish up by saying, okay, so I've told you that supernovae can be dangerous if they're close. Let's talk about nearby supernova. And so now we're going to do archaeology, and we're going to need this amazing machine here. This is an accelerator, and this will come into play. Okay. So if a supernova is near the Earth, it rains its guts on us. So let me explain how this works. So here's another image of a supernova explosion. It's an X-ray picture, so it's X-ray vision. And the reason you're seeing X-rays, the supernova material is launched at enormous speed, a few percent of the speed of light, and it crashes through interstellar space. And as it plows through interstellar material, it sweeps it up and slows down. This stuff eventually slams into the solar system, and now the sun, so here's an image of the sun. We blocked the middle kind of like during an eclipse, and you can see that the sun has this beautiful corona and this material flowing outwards. That's called the solar wind. And so the sun has material flowing outwards, and the supernova is crashing inwards, and so there's a collision between these two flows, these two winds. And so if the blast is close enough, then it overwhelms the solar wind, it pushes into the inner solar system, and supernova material rains upon the Earth. And then it accumulates wherever stuff accumulates, and so it accumulates in the deep ocean as well as ice cores. And so here's a little simulation we did to show you what this might be like. So now we're zooming into the solar system. So here's the sun. These colors are the solar wind. This is just the sun blowing its breeze out into the solar system. And I didn't draw the Earth, but I drew a circle where the Earth would be. So that gives you a sense of scale. This is where the Earth would be going around. And then I'm going to zap the supernova from below. So here we go. Here comes the supernova. Wham! And so the supernova is so powerful. This is a very nearby supernova, by the way. It blasts the solar wind back, and so then all this stuff is supernova material, and then the Earth is going around and around inside the supernova material. So how do we know? So I'm saying if a supernova is close enough, it will spew its guts upon us. How would we know? How would we know that possibly millions of years ago, supernova guts were brought here? So we need a fingerprint, something to say, aha, if I dig this up in the geological record, I knew it came from a supernova. And so clearly, the fact that these are nuclear reactors, we want a nuclear signature. It turns out, if you look at something stable that the supernova makes, I told you they make a lot of oxygen, they make a lot of silicon, so maybe I could just look for stuff made of oxygen and silicon. Well, it's not a good idea because the Earth was already made of stuff with oxygen and silicon, so that's a bad idea. On the other hand, if I find radioactivity, this is why I told you about radioactivity. The supernova makes radioactivity. If I find radioactivity that hasn't decayed yet, then there's no reason it should be here because it should have long ago decayed away, and that's how I know it came from a supernova. So you can make a list, and we did, of all the different kinds of radioactivity, and there's a particular kind of radioactivity we care about today, and that's a radioactive version of iron called iron-60. It only lives about 3 million years, which sounds like a long time, but the Earth is billions of years old, so anything the Earth was born with is long gone. So if you find it here, it had to be brought here. Okay. And the amazing thing is there's evidence for this. So this is what's called a ferromanganese crust. So this is a crazy thing from the bottom of the ocean, in fact, from the Pacific Ocean. It's called a ferromanganese crust. It's a fancy way of saying it's a rock. It's actually something that grows on top of a rock at the bottom of the ocean. So there's some rock, and then it starts to grab iron and manganese and other trace elements from the water and slowly grows over time. And so this black thing is mostly iron and manganese, a few other elements, and it grows really slowly, a millimeter per million years. And what you're seeing here is a picture of one of these. I've held it. It's very amazing. That's about the size of a quarter for scale. So, that rock's about this big, which means it's many millimeters deep, which means you're seeing many millions of years worth of deposits. And so we need to make ultra-high sensitivity measurements. And if you do this, lo and behold, live radioactivity was found here. They actually found that this contains radioactivity. And you might ask, what pattern do you expect to see? So here's the idea. This thing is growing, minding its own business. So boring, 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 regular iron, boom, supernova, boring, boring, boring. That's what you expect to see. But back in 1999, when this was first done, first of all, they couldn't slice it into many layers. Only 3 layers. They couldn't make a very detailed measurement. It wasn't a very level rock. And they found some amount of iron in all 3 layers. So they could tell there was radioactive iron, but they didn't have a good rock for finding out when the signal really came from. So that's bad. But then, in 2004, are using this big accelerator I showed you pictures of. These guys now had shown they knew what they were doing, so they got a better crust that was now well stratified, so you could really do this measurement, better time resolution, and when they did this, here's the data. So now I'm going to show you a plot, and so here's time before present amount of iron 60. So we're looking down into the crust, which is growing over time. So that's today, as you go deeper, 2, 4, 6, 8, 10, 12 million years ago, millions of years ago, which means millimeters. And this is amount of iron 60. And so if you stare at this plot, there's 2 things. So there's this here. This is background. So this is basically the experiment is never perfect, and so that means they can't measure anything smaller than this. This is just noise. But of course, the beautiful thing is you don't just see noise, you see that. And that is a big deal. Because that tells us there is radioactive iron, and it tells you when it was, between 2 and 3 million years ago. And so we found a pulse, we can tell you when it is, and the total amount of iron is radioactive iron is consistent with the old rock.
Excellent.
Also, you can't read this, but the amount of iron is amazing. It's 1 part in 10 to the 15. It's amazing you can do this. Well, in 1,000 trillion. Amazing. Okay, I'm already out of time. Liang's getting very anxious. Let me just tell you what happened in the past couple years. So in the past couple of years, we went from what I just showed you, this amazing measurement, now new data with new probes in new sites. And so let me just summarize. A different group using a different experiment in a different part of the world, in a different crust, found that there's also iron 60. Other groups, this group and another group, didn't just look at one of these crazy crusts, they looked at an ocean sediment. So this is an example of these cores that are at the bottom of the ocean where you dig up the mud, basically. So this peanut butter looking stuff is actually mud. It's ocean sediment. It grows much faster, 1 millimeter per 1,000 years. And if you look at that, it's a harder signal to find. But if you find it, it gives you more information about how the signal came over time, how the radioactive iron fell on us over time. And some of it actually even contains these magnetic little fossils, it's crazy, of bacteria that collect iron from the water, make little magnets that they use to steer around in the Earth's magnetic field. Apparently, if you hold a magnet to them, they swim around. You can torture them. And then they die, and their corpses are here, and that's a lot of where the iron comes from. And then, most amazingly, there's a signal from the moon. And so that's Alan Bean in Apollo 12. So Apollo 12, that's one after Apollo 11, after one small step. But before Apollo 13, Houston, we have a problem. And so Alan Bean is taking a core there. So he's got basically a tube that he's driving into the soil of the moon and pulling it out. And that soil was analyzed, and it contains iron 60. And then there's also cosmic rays, high energy particles from space, and those also contain iron 60. So in view of time, I won't bore you with showing you lots of plots of data, although I'm really tempted to, but Leanne's getting really anxious, so let me finish up. So we now really have confirmation of this, and you might ask, well, wait, what would this do? Well, it turns out the sun, do we have evidence that this really occurred from astronomical evidence? Well, the sun lives in a region of hot, low-density gas. And this is called the local bubble, because it's like a bubble, and it's a huge cavity, and to make a cavity this big, so this is an artist's conception, we live somewhere in the middle, and to make a cavity this big, you need nearby supernovae, something like 10 supernovae in the past 10 million years. And so astronomers have speculated that where the supernova might come from in nearby star clusters. And then finally, the supernova debris is spread out over space. So from the amount we measure, we can ask how spread out was it, and we can get a sense of how far the supernova was. And it's between 60 and 300 light years, which is, remember, The kill distance was 30 light years, so it's beyond the kill distance, but barely. So this is a near miss, and so there's even some chance it might have not caused a mass extinction, but been bad for some species, and that's kind of amazing. So there's a connection with biology. This is an artist's conception of one of our ancestors saying, uh-oh. So, yeah. All right, so let me finish up. Let me go to conclusions. So there's two steps to my conclusion. The most important conclusion is this is a thing. This is no longer a hobby. This is a thing. So this is now a new probe for astronomy, for astrophysics, for geology, even for biology. It's amazing. So now, let me give you sort of my outlook going forward, and by the way, mention all the people who actually did the work, my collaborators here, including my students. So, what have we learned? Live radioactive iron has been seen globally and on the moon, and we see signals 3 million years ago, and I didn't show you the data because we ran out of time. We now see another signal at 7 million years ago. There was more than one supernova. So, this is the birth of supernova archaeology, which isn't just important for astronomy and physics, but also astrobiology, life on the Earth and elsewhere in the universe, even evolutionary biology could have affected life on Earth. I don't want to give the impression there's nothing else to do in this field, so we'd like to understand more astrophysics, how the supernova produces these radioactivities, as you were asking, how it moves over space, how it finds its way to the bottom of the ocean. We'd like to understand the supernova production of radioactivity in the first place. That's a very complicated thing to calculate. And we would like more and different kinds of samples. We'd like other kinds of radioactivity. I didn't get to tell you, but now there's now a hint of seeing plutonium. And other sites. I mentioned lunar samples. We'd love to go back to the moon. I can tell you more about why it'd be really cool to go back to the moon. And other epochs. So I've told you, this was 3 million years ago. This clearly did not cause a mass extinction because we're here to talk about it. But an interesting question is, could a supernova be associated with mass extinctions in the distant past? And we don't know that, but this shows us we have ways of telling by looking for the radioisotopes. So we have the technology to try to address that question. So it's a really interesting field. Thank you for your attention on a beautiful Saturday, and stay tuned. Yes, sir. Oh, yeah, that's right, because I kept saying, so the question was, what is a great question, a really important question. What happens to the sun when it runs out of fuel? Because I kept repeatedly saying the sun will not die as a supernova. There are great science fiction stories about that. They're fun, but they're wrong. The sun will die in a much more long process. It will not be an explosion. It'll take thousands of years. But once again, the sun will run out of fuel. It will turn out, it will in a more slow motion kind of way, will spew most of its guts into space, but leave a crunchy center behind. That crunchy center won't be nearly as crunchy as a neutron star. It'll be called a white dwarf. So instead of being the mass of the sun and being the size of Champaign-Urbana, it'll be the mass of the sun and merely just the size of the Earth. So it still will be super dense, but not as super dense. So it will die, still spewing guts into space, new elements that other stars will eventually incorporate and other planets, but will leave behind a white dwarf. And we have, yeah, that happens about 5 billion years, but even bad news will start to happen in 1 billion years in terms of boiling the oceans. Great question. Please, in the red. Great question. So the question was, so by looking at the amount of radioactivity and saying, well, we know it's spread out over space, so from the amount we see, we can get an idea how far away it was. So we could ask, if we look out into space at these kind of distances, can we see the crunchy centers, the neutron stars left over by the supernova? And the interesting answer is we see a number, so these would be very nearby neutron stars flying through space, and there are some candidates. So there actually are candidates neutron stars that may be part of one or more of these explosions. So the answer is yes, and there's active research tracking that down. It's a great question. So because we have multiple nearby neutron stars, and so there's a detective work you have to do, track it back into time and ask where was it 3 or 7 million years ago, and that's still a subject of active research. There are candidates for that. So we may already have discovered them. Yeah.
The one on the very back?
Yeah, in the back, please. Oh, yeah, so that was a great question. So, or an observation, because I mentioned there's this funny thing. We had this supernova, this Crab Nebula 1,000 years ago, and why didn't the Europeans leave a record? And so one suggestion was maybe they incorporated it into their mythology. And indeed, maybe they did. So maybe they just had some other explanation. That wasn't a star, that was something else. But we, in the written record, we haven't found anything that looks like a discussion of an exploding star. But it remains a really interesting question. They surely must have seen something, and how did they think about it? That's a great idea. Thank you.
Because of time, we just have one final question.
Please.
I have a kind of a corollary question on this. Seems to me that time has to be nonlinear itself, especially if it has to be affected by extreme mass.
Ah.
Why not?
Oh, yeah. So that is a whole talk by itself. So the question was about time, and shouldn't time be affected by mass? And that is a whole talk by itself. But the answer is, you're in good company. Einstein said the same thing. So Einstein said, that's his theory of general relativity, that mass warps space and time, and near massive objects like black holes, time runs differently. And that's a whole talk in itself. But even in a less massive object like the Earth, that even affects the flow of time, and we've measured that. So, so that's what you say is exactly, that's a whole talk by itself. That's a great point.
Okay, you can come down to ask more questions.